Hello, everyone, and welcome to today's webinar, Reduce Vehicle Development Costs with Real-World Simulations. In this webinar, you will learn how physical testing can be replaced with accurate transient simulations to reduce costs, shorten design cycles, and discover higher performing designs. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is John Yuskevich. John is a thermal and CFD engineer at Thermal Analytics and has been a dynamic part of the engineering team since 2013. He received his bachelor's degrees in mechanical and biomedical engineering from Michigan Technological University and completed his master's of science in mechanical engineering from Oakland University. John's current research focus is on the development of transient thermal simulation methods for vehicle packaging studies. Throughout this presentation, you can submit questions in the questions box and we will review them at the end. We are also recording this webinar and we'll be sending you the link following this presentation. With that, John, if you're ready, you may begin.
Okay, thank you so much for the introduction, Chris. Good morning to everyone on the line. So as Chris already said, today's webinar is titled Reduce Vehicle Development Costs with Real-World Simulations. Before we go too far, probably makes sense to talk about what we're going to talk about. So I'm going to start by introducing kind of the modern solutions to the age-old problem and talk about why we really need to be focusing on transient simulations and how that relates back to our business as a whole. Then we'll talk about the million-dollar question and how do we start approaching that. And then I'll introduce the novel approach to drive cycle simulation, talking about the theory, the history, and the commercial solutions produced by Thermal Analytics. And then finally, I'll go through a brief case study and follow it with some conclusions. So starting with the modern solutions to age-old problems. It's not a surprise to anyone that growth in a business is good. That always leads to happy business people, higher pay, increased investments, more interesting projects, and as most of the engineers will say, the all-important thing, happier engineers. But as engineers, how do we actually create that growth? So if we think about the typical investments and the typical value of things that we can do, and we plot out our normalized return on investment, that lets us think about what we could be doing, where the bottom right on this chart, shown in red, are things that require a high investment and a fairly low value or low return on investment. Whereas the top left shows items that are going to be low cost and offer a very high value. From here, we can start to look at the different things any given business can start to do in order to provide new value. These include things like reduction in physical testing costs, performance improvements, converting funnel opportunities from the bottom or the top of the funnel, creating more opportunities through marketing campaigns. But you'll see many of these things aren't things that an engineer can directly influence. So if we pull those out, we're really only left with 4 options. And there's one of these that's clearly miles apart from the other 2, and that the reduction of physical testing. This offers the highest return on investment because it's one of our highest cost options. If you think about what it takes to do physical testing, either you've got test facilities with dedicated staff, they're expensive to build, they're expensive to maintain, testing costs are very high, or if we're not doing it at a physical test site, we're probably moving that vehicle to different locations around the world, which incurs travel costs. We still have vehicle preparation costs, costs associated with instrumenting the vehicle. So obviously there's many things that can be reduced here. And that's compounded by the fact that we're not talking about 1 or 2 test cycles. We're often talking about dozens or hundreds of different test cycles that have to be executed in order to complete our design. One wonderful thing about this, though, is that if we can reduce that physical testing cost, we can also influence the cost of other options. So by reducing our physical testing costs, we can start to reduce the design costs because we're doing less physical testing and can do iterations more quickly. We can improve the performance because we can do many more design iterations. And if we apply what we've learned in simulations to the durability of a vehicle, we can start to reduce our warranty costs. So thinking about that just in the realm of thermal test cycles, we're always trending towards kind of real world cases. If we think about where we're at today, on the left-hand side, or our y-axis, we can see the simulation method maturity at most OEMs. And then on the x-axis here is test cycle complexity. So the one that's fairly straightforward and most OEMs are doing today are these steady state analyses, which is really a fairly easy thing to accomplish, but we're moving away from that as our designs are getting better and better, and we're required to do more and more testing. Now today, we don't just talk about a steady state temperature or a peak load temperature. Instead, we talk about things like a peak excursion test or thermal soak conditions, where we drive the vehicle, then come to a quick stop and key off and let the parts rise and fall in their natural progression. In addition to that, we've got a number of simple derived cycles, things like emission cycles, like the WLTP, the FTP, or things like the trailer tows, like the Davis Dam, which is also known as the SAEJ 2807 test. And then if we're talking about high performance vehicles, things like racetrack vehicles or high-end consumer vehicles, we want to make sure that we're getting good performance out of the vehicle on things like racetracks, things like the Nürburgring Ring or the Autobahn test cycles. And then we still have things that are much more focused and are closer to real-world use cases, things like delivery vehicles or cyclic loads, school bus routes, city cycles, where we have repeated driving and then idling and driving and idling, or things like the multi-stop brake cycles. What you'll notice is that most of these tests require some transient simulation in order to approximate. There's no way to approximate these 4 tests with a steady state representation and maintain a high level of accuracy. Furthermore, we have to keep in mind that things like that steady state simulation or that steady state test are engineering approximations of end customer behaviors. And in reality, customers are doing things that look a lot closer to that mixed cycle or those high performance cycles. So we need to be able to address that in order to design the ideal product for our end customers. That's why we've seen over many years the modification of design targets. And in a simple sense, we can think about things like the high ambient temperature or low ambient temperature on one axis and the engine load on the other. And it's pretty obvious that we often design around the thermal worst case, which is where we have both a really high ambient temperature and our max engine load. The issue with that is that that's a very extreme case. If you imagine driving in the desert at max speed for really long periods of time, that happens sparingly. Instead, most customers spend most of their time far away from that. And as a result, we talk about design metrics that are some function of the worst case and the typical operation. Translating all that into a more practical example, we look at the results of this test. We can see that our thermal worst case happens once in the test cycle and happens at 150 C near the very end of the test. Meanwhile, during the warm-up period, there's a fan-induced temperature cycling that's causing all the temperature components to rise and fall very quickly and very cyclically. And that oscillation is about 110 to 130 degrees C. The question then becomes, which one of those 2 conditions actually causes that part failure? Does that fan-induced temperature cycling cause more damage than the thermal shock caused at the very end? And the only way to know that is to do these transient tests, characterize the temperature profile, reduce that to a cyclic cycle, and then apply that to a structural model and compare that to the peak excursion temperature stress and determine which one of those 2 conditions is going to cause the most likely failure. And that brings us to the million-dollar question and how we're going to start to approach it. So now that we understand that physical testing is very expensive and that we always have to be driving towards what customers are actually doing, whether that be the actual customer use cases or things like emission cycles that we're required to do by law in order to make sure that the design is valid. The question then is, if we need to reduce our physical testing costs, is it possible to simulate a test cycle like this today? If at your organization the answer is no, it's probably because the simulation times are far too large, or that the low-cost simulations that are viable in terms of runtime aren't accurate enough to be predictive. If yes, there's always the question of how predictive is it? Is it predictive enough to be valid in a digital sign-off environment so you can reduce your physical prototypes? And are you using your limited resources to their full potential, whether that be in terms of CA tools, HPC resources, or engineering know-how? You want to get the most out of all those resources. So think of how we would approach that. If we limit our focus just to the 2 most complicated test cycles, that mixed duty test cycle or the high performance or dynamic driving test cycles, we can think about putting what we are after in terms of a high accuracy, the low cost, and a fast turnaround time. The most common tool in the market today are what we call multi-physics tools. These would be your all-in-one CFD tools or your all-in-one CAE tools, which have really high degrees of physics accuracy, but are computationally very expensive. They're very complicated to use, so they don't offer that fast turnaround and that relatively low cost. There are other options that start to reduce some of that accuracy by segregating the thermal and structural domain, most notably the pseudo-transient and the stepwise coupling, which I'll talk a little bit about later. Sacrifice some accuracy in the solution, but pick up a significant amount in terms of the turnaround time, which allows us to simulate these test cycles, but it's not the most efficient use of our resources. On the other extreme, we might have things like system analysis tools or 1D tools. The benefit here is that they're really fast, they offer a fairly low cost, but they're not predictive, so you give up a lot of accuracy. So we're really looking for something that's somewhere in the middle, and fortunately, we happen to know that there is one. There's something called a surrogate model cosimulation method, which is what I'll talk about for most of the remainder of this presentation. The benefit of this approach is that it balances both the cost of running a simulation, balances the runtime involved, and maintains a high degree of accuracy. So we finally found this nice Goldilocks solution that balances all three. So now I'll talk about what that approach is, and I'm going to start by talking about what the theory is and do a little bit of an introduction to the history and some of the publications that are available, and then I'll talk about what the thermoanalytics approach to that problem is. So from the theory side, we always start with some representation of the vehicle boundary conditions, and this most often comes in the form of a vehicle speed and road grade profile. We then translate that to get a representative set of vehicle parameters, and this can range from everything from vehicle speed to exhaust gas temperatures, engine load, or even the grille shutter positions. We then use all that information to calculate a series of steady-state conjugate heat transfer solutions at each selected speed or at each selected vehicle parameter set. Then we extract out the heat transfer coefficients and fluid temperatures, which are now at these discrete points for each sampled location, and use something called a surrogate model to make those discrete points continuous. You can think of a surrogate model as a really, really nice interpolation model. And all it's doing is taking these discrete values that were at each representation or each selected parameter point, which is broadly referred to as a sample point, and then finds a way to make those continuous so that we take, say, 5 to 10 sample points, and then we can characterize the entire drive cycle. And then what we do is we take that surrogate model of the convective boundary conditions, that heat transfer coefficient and fluid temperature that's been made continuous, and then use that to solve the transient thermal simulation. This is actually a fairly old technique. It was originally proposed by Dr. Kaushik at GM Research. He demonstrated that you could take a vehicle test cycle, such as the one shown here on the left, characterize it with as few as 6 operating conditions. He used an optimal Latin hypercube and a Gaussian Kriging model to then calculate part average heat transfer coefficients and fluid temperatures, and then simulated those parts in a transient thermal model. And what you can see here in that black line is the analysis method or simulation method compared to the light gray line, which is test data. And you see that there's good correlation overall. This particular example is coming from a rubber engine mount. This was extended by Pryor in 2011, where he showed that you didn't even need to limit it to these kind of short duration test cycles. He showed that you could apply the exact same method with fewer inputs to a much longer test cycle. The cycle you're looking at here is a commercial vehicle doing a delivery cycle where it drives 4 hours out, takes about a 30-minute break, and then drives the same 4-hour path back. Pryor showed that you could use vehicle speed, the fan mass flow rate, the fan air temperature, the fan blast temperature, and the exhaust gas temperature to characterize all the convective boundary conditions needed. He selected those with a manual method and then fit those with an inverse distance weighting to make them continuous, then applied those to his transient thermal models. Here you can see in the dashed burgundy line are the test results, and the gray line is the inverse distance weighting simulation. You'll see it again, we get very good correlation for a fraction of the computational cost. And then finally, in 2014, Dr. Hendel at BMW Motorsports demonstrated that you could apply this same method to characterize multiple drive cycles using a single set of input parameters. Furthermore, he showed that the convective boundary conditions are almost entirely governed by the vehicle speed, and this is especially true in high-performance vehicles. Now, his selection method was never disclosed, but the interpolation method was revealed to be a simple linear interpolation of the vehicle speed. These are then used to create the local heat transfer coefficient and fluid temperature models, and then can then be applied to highly dynamic vehicle test cycles. Here you can see an example of that, where we've got the exhaust and underbody, and you'll actually see as we move through the cycle, there's very large temperature swings, especially as we go from high to low speeds. So all that said, this is obviously a fairly complex process. There's a lot of selection of sample points involved. You have to calculate conjugate heat transfer solutions, create your own surrogate model, and solve a transient thermal solution. Fortunately, this process is entirely automated in thermoanalytic software Cotherm. We market this under the product name, the Drive Cycle Extension. What this allows you to do is take in your test data directly from Excel and then process that so that you can remove some of the unnecessary data. From here, we'll help you select the representative vehicle states, either using an optimal Latin hypercube or full factorial sampling, and this can be supported in any number of dimensions. From there, you can even visualize how those sample points interact with your boundary conditions to make sure that you've selected enough sample points and that those sample points cover the entire range of vehicle operating conditions for all the test cycles you're interested in simulating. Using that data, Cotherm will then automatically calculate all the conjugate heat transfer solutions needed in order to characterize the convective boundary conditions. And then those are automatically converted into a surrogate model in Tytherm. All the relevant boundary conditions for a test cycle are imported into Tytherm, and then the thermal tool, in this case Tytherm, automatically then calculates the test cycle. And this is then extended so that any number of test cycles can be specified, whether that be a single test cycle or 10 test cycles. The process is always the same, and it will always let you do these very long transient simulations, characterizing everything you need. So moving on, I'm going to talk next about a case study where I'll compare some of the different strategies for coupling these tools. This is an excerpt from a 2018 TMSS presentation entitled Strategies for the Simulation of Thermal Test Cycles in 3D. The process, or the study itself, looked at 3 different representative speed profiles. You can see those shown here, where the one on the left-hand side is the test cycle we've shown previously. That's 9 laps of the Nuremberg ring into a key-off soak. Cycle 2 is a standard EPA test cycle, and cycle 3 is our typical 2-step speed change into a key-off soak. This would be one of our normal extreme use cases. Most commonly, we can approximate the cycle 3 with steady-state runs because of its really long duration. What was done is those 3 speed profiles were fed into a GT3's system model in order to create representative 3D boundary conditions. These boundary conditions are things like the inlet speed and inlet air temperatures after the fan zone, and then internal convection for the engine bay or components on the interior. These test cycle boundary conditions were then fed into a conjugate heat transfer solution, an all-in-one tool, to establish a true solution. And from there, we use the same boundary conditions to simulate various methods for segregating the domains and look at how efficient those coupling strategies were compared to the conjugate heat transfer solution. And then finally, we compared the conjugate heat transfer and coupled solutions for runtime and accuracy. The geometry we used was based on a simplified engine bay found in other publications. This was converted to a 2-dimensional form shown here. And what we have in the very top is the head, the manifolds, the block, and the case. These were all specified with those boundary conditions generated from GT. Here you can see an example of the heat transfer coefficients and fluid temperatures on the interior of one of the engine components. The inlets and outlets were defined as an inlet on the inside downstream of the fan, and then we have pressure outlets located at the bottom and rear of the compartment. You can see on the left-hand side the inlet speed and the air temperature for one of the two test cycles. This is data from test cycle 2. This was then repeated for all 3 test cycles to establish both a true solution and a comparative solution. But for the sake of time and for the sake of this particular presentation, I'm going to limit all the further discussions just to cycle number 1. This cycle had a total duration of 1,350 seconds. It has a max speed of 38.8 meters per second with an average speed of 18 meters per second. So you can tell these are very high velocities. And you'll notice here that the volatility index is extremely high at almost 3. Looking at the true solution, you can see the velocity contours on the left-hand side and the air temperature contours on the bottom. What you'll notice is that things start out initially quite cool, and then they warm as the engine starts to warm up. And you'll notice that a lot of air is diverted around the engine. So you have some going right out the very bottom through that pressure relief on the bottom of the engine bay. And then we have a fair amount of compressed flow at near the top that kind of wraps around the rear of the compartment and finally exits to the rear pressure outlet. On the right-hand side, you can see the results of that simulation looking at a 6-node average on the manifold on the front exterior side. You'll notice that it starts out at that 300 Kelvin mark and then very quickly climbs up to a near steady condition, but never quite reaches that steady operating point, which again gets back to why that transient is so important. There's no way to approximate this same behavior with a steady state model without over predicting the temperatures or having to make assumptions that deviate from the actual operating conditions. The first method we explored was using a stepwise method. Now, this uses a transient solid domain defined by a coupling interval. And then at the beginning of that interval, we have our CFD solution. What we do is we pass the wall temperature from the transient solid domain back to CFD. The CFD solution then solves to give us the heat transfer coefficient fluid temperatures, and then we seed the wall temperature forward to the next coupling interval. This process is repeated at the end of each coupling interval, and then we repeat the total process until we get the entire test cycle simulated. Here you can see the results of those simulations, looking at 3 different coupling intervals, a 30-second, a 15-second, and a 5-second. If you look on the right-hand side in the boundary conditions plots, you can actually see why this is called a stepwise coupling. You'll notice, especially in that yellow line, there's a very obvious stair-step type shape where we're following the boundary conditions a little bit, but there's very significant differences. And you'll see that in both the heat transfer coefficients and the fluid temperatures. But if we look at the wall temperature on the left-hand side, you can actually see it's a fairly accurate solution method, noticing that it's only a few degrees Kelvin off of the true solution. And there's actually not very much impact in terms of the predicted wall temperature based on the boundary conditions or the coupling interval. That said, there are dramatic differences in terms of the runtime. So if we look at this plot on the left, the simulation time, that simultaneous CHT, is the simultaneously solved conjugate heat transfer solution. That's our true solution. You'll notice that it is orders of magnitude more computationally expensive in terms of CPU seconds than the stepwise methods. The stepwise methods also allow us to make a distinction between computational fluids and the thermal structural domain. You'll notice again that in all 3 cases, that computational fluids domain is much, much more expensive to compute than the thermal structure. This indicates that using a thermal structural model would be a much faster turnaround time. And what we really need to do is find a way to simplify those computational fluid runs to help reduce the runtime and computational cost. In addition to that, if we look at the plot on the right and compare the actual accuracy over the whole test cycle, you'll see that there's almost no difference between those 3 different coupling intervals. This indicates that, especially at these highly dynamic cycles, you're not likely to gain very much by reducing your coupling interval to something very small, although you will pay a large penalty in terms of runtime. One related method to this, and what we tested next was something called the pseudo-transient coupling method. This is almost the exact same method as the stepwise method, except instead it loops between the start of a transient domain and the second CFD point for each coupling interval. This allows you to introduce an interpolation between the first coupling point and the second coupling point, which in theory provides a more accurate representation of the boundary conditions. Here you can see the results of that. where in purple we've got the pseudo transient run, and then I'll introduce the stepwise so we can get a comparison there. If we look at the heat transfer coefficients, we'll notice that the trend is much better when we look at the pseudo transient. And in the fluid temperature, we do pick up more steady state air. But overall, if we look at the wall temperatures, we actually show that there's a slightly better correlation. Noticing that in the beginning of the period, about times before 400 seconds, the accuracy is just about the same. But once we cross the 500 second mark, the pseudo transient method provides a significantly improved accuracy. Next, I'll talk about the surrogate model cosimulation, which, just as a reminder, what we're doing is we're selecting a set of representative sample points, using those to characterize the convective boundary conditions. We calculate our steady state conjugate heat transfer solutions, build our surrogate model, and then run our transient thermal model. And all of this is automated in the Cotherm toolkit. Here you can see the results of that run. In red, that's the simulation data, and in black, that's the true solution, our conjugate heat transfer solution. You notice that, again, if we look at the wall temperatures, we're getting very good correlation. There's a slight overprediction in the beginning and a slight underprediction in the second half, but overall, very good correlation. If we look at the heat transfer coefficients, you'll see that we get a very, very good approximation, especially in areas where the rate of change is fairly uniform. You'll notice that we are picking up some noise from the boundary condition signal, but it's minimal and it happens so quickly that it doesn't have a strong impact on the wall temperatures. The fluid temperatures, on the other hand, do show a much larger steady state error, and they don't perform very well when we get into that key off soak condition. But as you can see from the wall temperatures, although there is a significant difference there, it's small compared to the rest of the boundary condition, so we are getting very good accuracy. Comparing those three methods in terms of the accuracy, you can see that all three are right around the 2.5 Kelvin mark, noticing that there's not a very big spread on that data. Overall, all three methods provide a very high level of accuracy. Where you do see very significant differences is in terms of runtime. You'll notice here that the drive cycle method, or that surrogate model cosimulation, takes the smallest amount of resources to actually compute, followed by the pseudo transient method, the stepwise method, and then finally that conjugate heat transfer solution. The advantage of that is that the drive cycle method is 34 times faster than a conjugate heat transfer simulation using the exact same models as inputs. That means that there are 34 more design iterations that you could complete, or 34 more tests that could be completed using the exact same resources and the exact same models. Furthermore, this is talking about a single test cycle. Because the drive cycle method lets you simulate multiple test cycles using a single surrogate model, you can expect much higher rates of return as you add more and more test cycles. But finally, I'll move on to conclusions. So it's not a surprise that reducing physical test costs is one way to create great growth opportunities. These transient modeling capabilities are a huge opportunity in terms of reducing that physical testing costs. And TAI's drive cycle extension enables you to simulate any test cycle in a highly automated fashion with a high degree of accuracy and low computational costs. There's a long history of using these methods, or the surrogate modeling method, in engineering design. They've been proven to be low cost and very accurate. And TAI's Cotherm software makes this process simple and easy to use, and it's highly developed, it's easy to deploy, highly automated. And then finally, the use of these surrogate models for convective boundary conditions greatly reduces the total simulation costs, while maintaining a high degree of accuracy compared to the other simulation methods available to us. And that this reduction in runtime allows us to do a greater number of design studies or simulate more test cycles. With that, I'll conclude my presentation. I'd like to open up for any questions that you might have.
All right, thanks, John. Yeah, we had a few come in. First off, does the type of heat transfer coefficient Y+, for example, calculated by the flow solver impact accuracy?
Ooh, that's a great question. Naturally, it does, because all heat transfer coefficients are some approximation of the heat transfer rate. So that selection does make a difference, but that will come down mostly to the modeling paradigm and a lot of choice by the user. Cotherm supports any type of export, whether that be the local heat transfer coefficient. You can use a reference heat transfer coefficient or the Y+ method as you've described. All of those will work just fine within this paradigm, but I'd suggest that we have a more detailed conversation about what physics are at play and what your meshing paradigms are before I give you a definite answer, but I'm sure we could use that method.
Okay. Are there any test cycles that couldn't be simulated?
None that I'm aware of. I'll put the engineering asterisk there that I'm sure I haven't seen every test cycle in the world, but I've yet to find one that we couldn't find a way to simulate using the drive cycle extension.
Right. Does this process support HPC usage?
It does. So you can run this both on a local machine or deploy it to your HPC. Cotherm does support the idea of job schedulers, or you can deploy Cotherm directly on your HPC. So there are a lot of options.
Let's see. Which software are you using for the CFD simulation, HTC calculation?
So in the case study that was shown here, we were using star CCM, but we've done the same work with any number of tools, the most common being star CCM, OpenFOAM, and Fluent.
Okay. Can you estimate an acceleration factor between a real cycle and simpler cycle? Does it help prescribe a better, simpler physical test? And then he said acceleration factor. Yeah.
So I'm not sure I totally understand the question. To whoever that is, I'll follow up with you offline to make sure I'm giving you a complete answer. But in the short term, I think what's being asked here is, as you go from, say, a really complex test cycle, something like those high performance type cycles, and try and walk that back to a simplified cycle that might be, a couple of speed step changes or even a steady state value. There's orders of magnitude difference in terms of the runtime for those types of simulations. The important thing to consider is just how accurate that simplification is. In terms of a specific number, I wouldn't be able to give you one now, but I think if we had another conversation and we could talk a little bit more about what those test cycles are and how we could discuss how you could simplify them and what types of runtimes or accelerations you might expect.
Okay. Yeah, I'll flag that one and save that one for you, John.
Thank you.
Let's see. Is it possible to support multiple input variables like shown in the history?
It definitely is. So Cotherm supports any number of input parameters. There's a little more to it when you get into it. The workflow is just as straightforward, but you do have to be careful. There's often a tendency to pick, many different types of variables. So the hard part with going into these really high dimensional spaces isn't that you can't run them or you can't use them, but it's a matter of selecting the most appropriate variables and picking the fewest number of them that will give you the highest accuracy.
Okay. Looks like that does it for questions. So yeah, John, I'll save that one so you can follow up afterwards. And thank you everyone for attending today's webinar. You'll receive a follow-up email shortly after this presentation containing links to download the presentation slides and watch the recorded webinar session. Again, thank you for attending and have a nice day.